Hello, my name is J-Wallace, and this is my first lab for Physics 2. The purpose of this lab is to experiment with charges and see if we can calculate the force and charge from Coulomb's law and Newton's law. We experimented with the charge tape and found the strength of the tape and created a computational model to prove that our math was correct. Based on our math and the data we found that the tape was positively charged, and we found the number of electrons lost from the process of charging the tape. So in this experiment, we found a way to give a neutral piece of tape a charge, and we figured out whether this charge should be positive or negative by seeing how it interacts with other things in the surroundings. And we experimented with similarly charged tapes to create a hovering effect. As you can see in the diagram, we have one piece of tape, and we managed to get it to hover over another piece of tape beneath it, because they're positively charged and they should repel. And then using Newton's third law, we were able to calculate the force that the bottom tape was pushing onto the top tape, and we were able to find the number or the charge of the upper tape and the number of electrons displaced from the charging process. So there's some prerequisite information we need before we can calculate the electric force exerted by the charge of the tape. First, we need the tape's mass, which I found to be about 0.2 grams. Then we have g, or the gravitational constant. Then we have the electric constant, which is 1 over 4 pi epsilon naught, which is about 9 times 10 to the 9th. And then using Newton's third law, we're able to find that the net force exerted on the tape should be equal to all of the cumulative forces individually and then added up on that tape. And so in this system, it'd be the force of gravity coming from above, pushing downwards, and the force of the tape beneath it, propelling the upper tape upwards. And these two forces should be equal. We also know from Coulomb's law that the electric force is equal to the Coulomb's constant times the charge, or times two charges over the displacement between the two. So in our experiment and the computational model based off of it, we made several assumptions. The first of which is that there are only two forces in this system, the force of gravity and the electric force. And in our computational model specifically, the tape is being represented by point charges that represent the center of the two pieces of tape. We're also assuming that both tapes have the same value for the charge. That's because we use the same process to charge both of the tapes and they have the exact same measurements. And we're ignoring anything like air resistance in our lab. We have the calculations I did to finish the lab and for our experiment. So we know the net force equals 0 on the upper piece of tape because the upper piece of tape wasn't moving, it was levitating in the air. And that means that the sum of the forces, which is the gravitational force and the electric force from the tape beneath it, must equal each other. So knowing this, we can set the force of gravity equal to the force of the electric force. And then we can break down the electric force into q squared over r squared. And the reason q is squared and that it's not charge 1 times charge 2 is because the charge of both tapes should be around equal. So if you take one value and multiply it by itself, that's just that value squared. So then we do some algebra to manipulate it to where we're solving for a singular charge. And doing all of that, I got around 1.476 times 10 to the negative 5 for the charge of the tape. We can do more than find just the total charge on a singular piece of tape. We can also find the amount of electrons displaced by the process of charging the tape. So if we know the charge of a single electron, which we know to be negative 1.6 times 10 to the negative 19, and we take the total charge and divide it by that charge of an electron, then we should be able to get the approximate amount of atoms that have been displaced in this, or the approximate amount of electrons that have been displaced in this experiment on a singular piece of tape. We found that to be 9.225 times 10 to the 13th. And given that an atom has an approximate length scale of 1.10 to the negative 10, we can find the number of atoms on the sticky side of the tape using division. And then the amount of atoms on one side of the tape, once we find that, we can find a ratio of the amount of electrons lost to the amount of atoms on the sticky side of the tape. To create the code for this project, I modeled 2 point charges that are a centimeter away. I have charge A and charge B. These represent the two charged pieces of tape, the one that was floating and the one beneath that we were supporting. I simulated the gravity and found the electric force using the charge from earlier. So here you can see the video of my code in action. And you can see how the top charge isn't moving. This isn't a still simulation, it's actually like a simulation where it's simulating the charge, the electric forces of both charges, and it's also simulating gravity. But the top charge isn't moving because both the force of gravity is canceling out with the electric force of the charge beneath it. This further proves that my math on the explanation side was correct. So what if electrons had positive charge and protons had negative charge? Ignoring the massive scale changes to our reality, the main difference would be the tape's charge would flip sign. So in our experiment, the tape was positively charged, it then become negatively charged. And why is it important to handle the tape as little as possible? Well, when the tape comes in contact with your hand, the charges balance out. Because it's positively charged and your hand is usually neutrally charged. It's going to take charges from your hand to the tape, causing the tape to end up being neutrally charged, which kind of effectively ruins our experiment. This is the end. Thank you for watching my presentation.